Hello everybody, welcome to today's session. Today we are going to discuss about transformer, which is the neural network architecture responsible for so much of improvement on the language modeling or any sequence to sequence task, including the recent development of GenAI, GPT, the vision transformer and all of them. It is a continuity from our previous learning. The last two sessions in particular, where we discussed about self-attention, and the second one is the comparison between RNN and CNN, the application of CNN in NLP, and then what problem it solves. So if we have remembered those two, our session will continue from there, and then we'll be able to understand why transformer is required and how it helps. If you recollect that in our last session we discussed about there are three factors which influences the efficiency or the effectiveness of a sequence to sequence model. So they were presented in this format where we said that when you are performing a sequence to sequence modeling, how many sequential operations are there. When it is recurrent neural network, we understood that it grows as the number of sequence increases, the sequential operation also increases, so which is a problem. We discussed all of this in our past videos. It will lead to more training time, it will lead to vanishing gradients. It's a trouble to train model with a long sequence. When we introduce CNN, it is constant. As you can see, it is big O of 1, which means it's constant. So it is not dependent on the number of sequences, right? Now, when we go to the maximum path length, then we see recurrent neural network to understand the dependency between the words, between the sequences. As the new sequence is coming, the network also expands towards the time horizon, right? When it is CNN, it has got the problem of only it can capture only the receptive field, right? You remember, it can only capture the neighboring points, but not the global dependencies. And if we have to solve that, then we have to stack more CNN layers, right? And that's how it would also increase, right? But it is improved version. When you go to the next one, which is computational complexity, we see that CNN computational complexities are more because there is a kernel factor which gets introduced into this one, right? Now from there, transformer architecture comes from here, which was published in Attention is All You Need, is the paper which was published in 2017, and it was a work done by these 9 authors together. They were all from Google Brain, right? Actually the paper starts with this comparison that why the traditional RNN and CNN was not so effective for a large sequence, and transformer aims to solve this problem. Little bit deviation from here. 2 authors from here are actually from my country, India. It inspires me. Ashish Vaswani, see how he started his career. You can see he is from your neighboring college, BIT Misra, went to University of Southern California to complete his PhD. Nikki Palmer started her education from Pune Institute. She moved to University of Southern California once again to complete her master. And you can see that she has obtained a very diverse experience, starting from database specialist, went to software development engineering as an intern, and then joined as a research scientist from here. There are 7 more very professional people. You can go through their name in the LinkedIn and find out what is their career graph. But I just touched upon these 2. Many of you might be already studying in this college. That may inspire you. Last video, we discussed about the dawn of self-attention. That was the name of the video, right? Where we discussed about when it is not machine translation, but we want to get the meaning of the sentence itself, then the encoder itself could have sufficed the architectural requirement. And in those cases, it is more important to understand how one word relates to other word. That gave the birth of self-attention, right? So in the self-attention, the mechanism was that as the sequences would appear in a RNN setup, it will do a mapping between the previous hidden state and the current hidden state, and like that it will keep on moving. As it moves up, we will have the attention function, which is a function of the current hidden state, and we are interested to identify how this current hidden state is related to the previous hidden state or the previous words. So that's what it just says here, right? However, you are noticing in this that the attention mechanism is working within the setup of RNN, right? And RNN has its own problem, which is the recurrent nature, the vanishing gradient problem. So how could one solve this problem? By not getting into a recurrent nature, possibly. Just capture the self-attention, which is the word and its relation with the previous word. That's the self-attention. Transformer is basically this, that you self-attention, it says attention is all. You don't need the RNN. Now, or the CNN for that matter. So transformer architecture, if you look at here, you see that was also in the same setup of encoder and the decoder, and you can see there is a inter-attention, that what we learned in our dawn of self-attention video. This is what is also known as cross-attention, is still in play in transformer. So what is changing in that case? The first thing we notice that there is something called multi-head attention, which is getting introduced here, right, in this architecture. We will come there, okay? This is a extension of the self-attention, and then it is proposing that we don't want to use the recurrent nature. But previously, this recurrent nature was naturally capturing the order of the sequence. Which word is coming first and which word is coming last, what is their order, that the RNN inherently that captures those information. But if we have to remove this from there, then we have to somehow give a information which is called the positional encoding. What is the position of the sequence that we have to add along with our embedding, and that's the second new thing we are noticing in this entire architecture. We will learn each of this block one by one. In today's video, we are going to start with the positional encoding. As you see, that's the first block here. Now, why positional encoding is important to understand that, let's see this sentence, which is the cat chased the mouse. Now you see, if the positions are not in order, the entire meaning of the sentence will change. For example, here, if these are not sequenced correctly, what happens is that the mouse chased the cat. It will be opposite, right? If you come here and if you say, they do not know that we are coming, if you don't maintain this but reorder them, then the meaning changes. They do know that we are not coming. Therefore, this sequence is very, very important. In the paper, attention is all you need. They mentioned the application of positional encoding in this research paper, which was from Facebook research. If embedding is basically this one, W1, W2 and Wm, and X is the original word, they are adding a positional encoding vector along with this one, W1 plus P1. So W1 is the embedding vector and P1 is the positional vector which they are adding here, right? So taking cue from here, those authors implemented it very innovatively, and we will see how it is. How one can encode those positional information. Very simple. Straightforward one could be that if you just do a linear formula of Fp is a constant and the position, then that gives you this kind of straight line. If it is an array of numbers, then each of their index position 1, 2, 3, 4 and all of them actually a positional encoding, right? So if a word is given along with their index position, that itself is a positional encoding. However, with that we have a problem. The problem is that monotonicity. This is monotonically increasing, which means as the sequence length increases, we will have a very large number to represent their position, and large number in the numerical computation creates problem. Numeric instability, gradient vanishing problem and exploding problem that we discussed in our previous sessions, all those will come into picture if it is not controlled. We could scale it, but then the scaling will also depend. So based on the vocabulary, the scaling pattern will change. And for a variable vocabulary or a variable sequence, the scaling will be difficult. Second, it may be discrete in nature. It may not be continuous, as you can understand. There are 1, 2, 3, 4. Therefore, there could be problem in terms of differentiation. To solve all this problem, what the authors proposed is their positional encoding will be with this formula. It's a periodic function. Instead of a linear function, they proposed a periodic function to represent the position. Now, it's quick recap of the sine and cosine function. The function is y is equal to sine of x or cos of x. We will first learn about the sine of x, and as you can see that the nature of the function is such that if x is represented by 0, then the amplitude of the wave also is 0. When it goes to 90 degree, which is the pi by 2 radian, then it reaches its maximum value. The amplitude goes towards the maximum, right? It touches the peak. The amplitude here in this case is 1. That's how we can call it as standard sine function. So when it is 2 pi by 2, it is 0. When it is 3 pi by 2, it goes to the trough, it goes to the minimum, and then it completes its cycle at 2 pi. T is the time period, lambda is the wavelength, which is 2 pi. And then a reciprocal of this, of the 1 by lambda or 1 by t, is the frequency of this graph. So this frequency can be increased by changing these values, which is, as you can see, that if we double this frequency, 2 times of this frequency, then you can see the nature of the curve. It is basically repeating twice and within the same time period. It is repeating twice, right? When you go to the cos function, we see it is exactly opposite, which means when it is 0, sine was starting at 0, but the cos value will be 1, right? Amplitude will be maximum here. So they are inverse to each other, right? By altering the value of x, we can also alter the frequency, and then for each frequency will represent a waveform like this, and they in turn can represent a position. Okay, so let's understand this one, which is a position. So we can let's say the sine, and the entire x function is, let's say, this one. So we assume that there is a 2 pi, and this 2 pi can be multiplied by this factor, which is position, by a constant number. So when the position is, let's say, 2, the second position, we get this value 0.588. When the position is 4, we get 0.951. When the position is again 9, then we see this value is repeating. That's how it will oscillate. The periodic nature will say that your the position here, the fox and dog, had it been linear, it could have been very far away. It may not be a correct representation of their distance. But when you are coming here, we can see because of this periodicity, some of the word may repeat. For interpretation, we can understand they are actually close by. Like this, that if this is the word, the quick brown fox jumps over the lazy dog, because of the periodic nature of the curve, we are saying that the fourth word, which is the fox, 1, 2, 3, 4, is amplitude wise almost similar, right? So that's how periodic function may help. In reality, when we are applying this is not exactly what will happen. Our benefit will be more of a containing this the value between -1 +1. That's the nature of sine and cosine curve. It will be continuous. As you see the values, they will be continuously changing. As a result, it will be easy to differentiate those functions. Then, as we said, that it will not really depend on the vocabulary size. Cyclic repeat we already discussed about. Now all this we have discussed when the value of this word, these words are represented by a scalar number, but it is not so. like we know that actually the words are first embedded, right? From our previous video we know that the representation of the word is a embedded vector. To comprehend that fact, let's look at this table. So these are the position, a quick brown fox jumps over the lazy dog. These are the position and these are the word. However, the word is not a scalar number, that we already know. Word is a 512 dimensional vector. Now for each of this vector we apply that theory, apply this formula which those authors proposed, A. Vaswani and others proposed here, that it will be a sine of the position. So position is 0, and then you are saying 2i. What is I? I are this dimension from 0 to 512 is represented by I, and then the D model is the 512, right? So basically, and 10,000 is a constant, is an empirical value which they have identified through the experimentation, that this works well for the sequence to sequence position embedding, right? Now what is happening here, that then we are saying position embedding is a function of position, and I is their embedding dimension. So look here, basically since this is 0th position, we are putting 0 on the numerator, and this I we will change as we changes this along this dimension, right? Because quick is represented by embedding, right? And along the embedding direction, this I we will vary from 0 to, you see, 511 and then 512. What is going on here, as you can understand, the quick then is represented by a vector. One vector was the embedding vector. Now we are also able to get another vector which is values for each of these components for the embedding dimension. Similarly, for the dog, this position becomes 8. Now this is not 0, so this is 8, and this becomes 0, this becomes 1, and this is 511, this is 512. So you can now visualize how for dog we will get a vector which is a positional numbers, right? What is happening here is, you can see, that's why we discussed about the nature of the sine or cosine function, where we saw that within this parenthesis there is the x, or that was basically the frequency. This portion, as we know, that f is equal to 1 upon lambda, right? Therefore the lambda I can be represented by this formula, which is 2 pi n to the power 2i by d, which is nothing but a geometric progression, which makes the lambda fall between 2 pi when I is equal to 0, this position or this position, then this is n to the power 0 becomes 1. So that is essentially 2 pi. When this value is very high, it becomes 1. So n to the power 1 then becomes the 2 pi n. Tells you that this is a sufficiently large range within which you are able to generate some numbers, and then these numbers will be little different because these positions are different. Here it is 0, here it is 8, like that. For each of this position they will be able to give you a lambda, giving you a positional curve for each of this position, but they are unique. How do you implement it here? You can just see this is the small code. We discussed about a I, which is this I, this I, we are making it as vector. That's why it is a capital I, right? It goes up to the d dimension. So there are 512 values within the vector. That's why the np arrange is up to d. Then lambda, which is nothing but np dot power, which is n to the power. We are just coding this formula, right? And then we generate the sine value of this one and then plot it. We get a series of number, 5 on 2 dimensional vector, that's what we get. And if we plot them, okay, from 0 to 9 we just wanted to plot here. So first one, if we take I is equal to, let's say, 0th position, we are generating the position curve for 0th position, we get this one, right? Because the position is 0, all of them becomes 0 here, sine 0. Now once we move to the 1, the first position, you see this number then represents a curve, a wave, right? And like that for position 2 to position 3, 4 to 8, for each one of them it has generated a unique set of number which can be represented by a unique wave, a unique frequency which has generated a unique wave. You will see from our code that it will, end of the day, it will generate a image like this, where from 0 to 2000, if this is what we think about our position, for those position, and this is the depth direction, the embedding depth direction, then for each of this position it will have a vector that can be plotted like a wave, and these are the wave, as you can see. As you go towards the higher value, you can see that wave, and this is nothing but the representation of, let's say, 1750's representation is this particular wave. Okay, now add positional encoding with embedding. How is it happening? Just a visual representation before we go to the code for this. So these are our sequences, which is up to the T range. This is the word embedding representation. Each word is now encoded, or rather embedded, with a 512 or D dimension vector. Then we pre-generate a up to L length. We don't know what will be the sequence length, so we take a sufficiently large number of sequence, which could be 2000 or 4000, and pre-compute the positional encoding. Then whatever sequence is coming, or the maximum sequence, whatever it is, sequence length, we strip it off from here. From the pre-computed encoding position, we need only T length. We slice that required positional computing for the word which is coming, right, incoming word, then add that with this one. Word embedding and the sliced pre-computed positional encoding is now added here. Together then they represent the embedding plus positional encoding is the value which goes to the transformer encoder. Now one more important thing which you have to remember, that our sequences will be coming with pad, because they are different length. Not all the sentences will have equal number of words, but we know that our model will expect them to be uniform. To make it equal length, we will pad them at the end. This was something which we had learned in our previous videos, right? Now those zeros, when is passed through the embedding layer, actually are no more zero. You can see that zero will have some meaning. Now we are coming to the positional encoding layer. Therefore we cannot depend on this zero anymore, because they are now represented by some values here, right? Let's say those values are 9 and 2, right? Together, now the final embedding also is not carrying the 0 anymore. They are actually the summation of embedding and the positional encoding. So 9.2 is 1 and 6 plus 2 is 8. So you cannot use 0 as the number to indicate that this is a padded position. This is really not, for this particular sentence, it don't carry any meaning, because they are now converted through the embedding layer and the positional encoding layer. To instruct the subsequent layer that you don't need to process this red color numbers, we pass this true and false as the mask value. Is a boolean array or a tensor will be also passed along with the final embedding, and this is what is called the masking information, which will be passed to the subsequent layer. in terms of code, what you do is to convert this 0 information as mask, true and false. All we need to do is, when you are doing the embedding, that time we just switch on this flag, which is mask 0 is equal to true. That will automatically create this mask. How it will create will just come there, and then when you want to retrieve whether what is the mask information, all we need to do is the embedding data, which is this embedding self.embedding. So if you go there, self.embedded data, okay, it is the same thing as the self.embedding here, dot underscore Kears underscore mask. If we call this hidden attribute, then it will give you the true false. So from this information, right, the vocabulary size and all, if you switch on this, it will compute this mask, and if you want to retrieve the mask, you just call this method. In fact, this happens automatically within the layer, because we will be normally using the Kears layer. Kears layer has a default method inside it. So when you are using embedding layer, you see there is a compute mask method. You follow that, and if you just look at the code, it is using any of. So you know that from Python that any will convert some condition, which is here in this case 0 or a valid number or 0. That's what they are checking, that if it is so, then you convert this as true and false. Very simple code, which is by default there within the Kears layer. You can see I have taken this from the base layer of Kears, right? And when you want to retrieve that information, which is this method again available, output mask, you see internally they are calling this attribute, which is underscore Kears underscore mask. So that's the hidden secret here, although you don't need to bother about all of them, but when you are doing your own implementation, it is good to know that Kears internally is also doing this trick. It's computing, actually converting 0 to a false, and then passing it to any other layer who will essentially call this underscore Kears mask method or the attribute. And here is a documentation which tells you, you don't have to go to the code, that if the mask is 0, whenever the layer is passed, for example, embedding layer will go to, subsequently will go to another neural network layer, which is for self-attention calculation, that time it should be able to automatically identify the mask. You don't have to do anything. Fair enough. I think that's what we spoke about here. In the paper, there is one more terminology which we need to be aware of, which is shared embedding weight. What does it mean? It means that this one, the input embedding here and the positional encoding, here it is the output. So for this input purpose, for the decoder input purpose, as well as for the decoder's output purpose, there also you need one more embedding layer, right, to convert it. For all three of them, the paper used a shared embedding. However, in our implementation, we will have separate embedding layer for ease of understanding. This shared embedding gave them couple of advantages. One is the regularization effect. Second is the encoder decoder representations are tied up, and this is particularly useful when there is a lot of similarity between the source language and the target language, which it is for a lot of European languages, right? They share a lot of common vocabularies, so there it would be good. Let's go to the code. So the first thing let us understand is the data portion. It is the same function, if you remember, we had used in our previous sessions. X1, X2 and Y. The X1 is our input data, the source language, which is in this case German. Then this is the English and this is the label, right? And then we have the tokenizer. In this case, you remember that we are using the tokenizer of the TensorFlow. We're keeping everything constant. The same data will only apply transformer here. The tokenizer will convert those word into sequences like this. They will be the numerical representation of those words. This is the source language, the target language, and the label. And as we know, they will be shifted by one position, while the input to the decoder will have start of sentence, which is 1. The label, which will be fed to the decoder, will not have the start of sequence, but will have the end of sequence, is 2. If you don't remember, go back to our previous sessions. This was very elaborately explained in autoregressive decoder. Now come to positional encoding, and as you can see that this is the class that we are using. So let's go to the imports and see. We have done this module. One is the encode pos, sin, cosine. Another is the positional encoding class. So let's open those modules. Okay, so when we come here, we just want to quickly update you about how the original, this is a tutorial on TensorFlow which you can learn from the TensorFlow website. It is their own tutorial. Why I have ignored this and then redeveloped entirely from scratch? One of the reasons, the first reason, you can see the positional encoding here is difficult to understand here. You see, their implementation is easy, probably less code, but where is those, even number will be sine and the odd number will be cosine? That's not really reflecting here. There were two sets of, one for sine, one for cosine, and little difficult to comprehend what is going on, all this. That's why the fresh implementation, you will see it is little easy to understand. What we are doing, as you know, this is our positional encoding. We already explained up to this portion, which is nothing but exact representation of the formula and then generating the the sign here. But the sign, as we said in our table, if you remember, that it will be for the even positions. So that's what we are using here by this notation. And the cosine will be for the odd ith positions, right? So as we move towards the increment the I along the embedding direction, every even position should have a sine value, every odd position should have a cosine value. So this is exactly what we have done here through this notation. And then we want to do the interleave. We first initialized an empty array, and within that you can see the even positions we are replacing by the sine values, and the odd positions we are replacing it by the populating it by the cosine values. Together they are giving the sine and cosine. Now this is a function, but this function will be now used within a positional embedding layer, which is inherited the Kears layer. And as we know, the Kears layer automatically inherit the masking capability, right? Remember that one. Now here, this is the place where we are doing the embedding, and inside the embedding we are turning on the mask 0 is equal to true, right? Then we are doing the positional encoding, which is calling this function which you have done here. After that, we introduce a dropout layer, because this is also proposed in the original paper, where all you have to plug in the dropout. So we have followed that and exactly incorporated the dropouts in every places as per the original paper. Then the compute mask method is what I was referring to, that the layer by default provides you this method which you can override. Yeah, actually we are doing overriding. We are saying that the self.embedded, from this layer you would have to do the compute mask and then return it. So compute mask will generate it by this parameter, and this layer, positional encoding layer, will return it to the next layer through this compute mask. Then this is where you are doing the call method, which when you pass the data it will be triggered. What it is doing is, first it is doing the embedding. Before that you ensure that they are a TensorFlow variables, integer variables, then passed into the embedding, which is basically calling this function. You are doing this square RT as per the original formula, right? The x is now scaled. After that, you are doing the positional encoding, and then you are doing the addition, right? You are doing the addition of embedding and the positional encoding together. Finally, you are adding a dropout layer here. So this is what is the x plus x self.position encoding is what you are doing. In another way, you are doing it more efficiently, which is also the addition. Then return the x. Now that's all about our positional encoding class. I will be providing a link to the code in my GitHub, but I will encourage you not to look at the code. You look at this video and then type in all this word by word, and then once it is implemented, you can go and compare with the GitHub code if that is required. Now go to the testing part of it. I pre-generate the positional encoding here, so it will be this curve which we have already demonstrated previously. And now let's do the PE class, initialize the PE class with my D model dimension, which is also the embedding dimension as 512. Then within the embedding data, you are doing the call method. You are calling the call method just by passing in the data, which is nothing but the source data first instance. That's what you are passing in here. The training is true or false actually controls whether dropout will be applied or not. Now when you print those embedded data, which is along with the positional encoding, you see it retains the original sequence length. Also it retains the dimension. From our PPT, we'll remember that they are adding the embedding, which is 512. Along with that, it is the positional encoding is getting added. So the dimension remains same, 512, and the sequence length is this. So for each of this sequence, we have a 512 dimensional vector, and within the vector, we have both embedding as well as the positional encoding, right? We are also now checking whether embedded data automatically carries the mask information. So yes, it does. These are the places, false are the places where there is no information actually. They are zeros, they are paired information. Where you need to focus, the model need to focus only on this true. That's the mask information which will flow through to our next session or the next layer, which will be focusing on the self-attention. So that's it for in this particular session. In the next session, we'll start from the self-attention building, then we'll also do the multi-head attention building, and then gradually build the encoder and then decoder, connect them together to build the entire transformer model. And all of them will do our own implementation first, then we'll also compare this our own implementation with the default implementation, giving you a solid, rock solid foundation of the entire transformer concept as well as code. See you then in the next video.